Hi, I'm Ravindu Nagasinghe from Honglu inside University of Artificial Intelligence, and I will present our work titled Why Not Use Your Textbook Knowledge Enhanced Procedure Planning of Instructional Videos, which is a procedure planning model that leverages rich procedure knowledge from a probabilistic procedure knowledge graph to assemble a strategic procedure plan. Procedure planning in instructional videos requires an agent to construct a logical sequence of action steps, thereby assembling a strategic procedure plan. This plan is crucial for navigating from an initial visual observation to a target visual outcome, as depicted in real-life instructional videos. This task serves as a step towards future where an agent like a robot can offer real-time assistance, such as helping people prepare recipes. Procedure planning in instructional videos has been first introduced by DDM. Building on this, P3IV replaces intermediate visual states with language representations for supervision. PDPP models the action sequence distribution using a condition projected diffusion model. Skip plan focuses on breaking down longer sequences into shorter subchains by skipping over less reliable intermediate actions. In contrast to previous work, our approach does not rely on annotations of intermediate states, natural language step representations, or procedure task labels. Despite the recent improvements in the task of procedure planning, current works face the challenges like selecting a viable plan out of all possible plans, given initial and goal states, extensive use of annotations, and inability to incorporate real-life knowledge in task sharing steps. To address these intricacies, we need a procedure planning model with minimal supervision that navigate the complexities of step sequencing and its potential variations. We propose KEPP, a knowledge-enhanced procedure planning system for instructional videos that leverages rich procedure knowledge from a probabilistic procedure knowledge graph. By using knowledge graph, we were able to better navigate the complexities of step sequencing and its potential variations. This approach requires only a minimal number of annotations for supervision, since it only requires knowledge graph paths and start and goal visual steps as inputs. We decompose the problem to prioritize the current available information and effectively incorporate procedure knowledge, enhancing strategic planning. In procedure planning, given an initial and a goal state observation, a model is required to plan a sequence of action steps, A1 to A10, to reach the indicated goal. To this extent, we decompose the problem into two subproblems. The first subproblem is to identify the beginning step A1 and the end step A10. And the second subproblem is to plan the intermediate action steps, given A1 and A10. Previous studies tackle this by harnessing detailed annotations in the datasets to offer supervision signals. In contrast, to tackle the second subproblem, we propose harnessing a probabilistic procedure knowledge graph, which is extracted from the procedure plans in the training set. Graph paths provide valuable procedure plan recommendations aligned with training domain, mitigating the complexities of procedure planning. Relying on training dataset paths, we construct a probabilistic procedure knowledge graph. In KEPP, given start and goal visual states as input, we adopt a condition projected diffusion model to identify the first action step and the final step. We refer to this model as the step model. Afterward, condition on this first step and last step and the planning horizon T. We query the graph to retrieve the relevant graph path from the procedure knowledge graph. Finally, conditional visual states and the procedure path plan recommendations are concatenated to predict the action steps using a condition projected diffusion model we coin as planning model. For both step and planning models, we use condition projected diffusion models with different conditions and padding sequences. In step model, to condition the diffusion model, we concatenate first and last visual states along the action feature dimension. During the dimension process, these conditional visual states can change. To prevent this, a condition projection operation is applied, ensuring the visual state and zero padding dimensions remain unchanged. In the planning model, same approach is used, while keeping the dimensions of the visual state, procedure knowledge graph recommendations, and zero padding unaltered. Infused procedure knowledge graph is directed and weighted graph created using the training data. In this structure, each step from the training set is represented as a node, while edges signifies the likelihoods of transitioning from one step to another. After queries are made to the procedure knowledge graph to find the highest probable path out of all possible paths, we multiply the probability weights of the edges along the path. Then top-par paths are selected as the recommended procedure plans from the probabilistic procedure knowledge graph and are aggregated through linear weighting into a single path and given to the planning model. We report the results for the dataset crosstalks, COIN, and NIV on varying planning horizons. Even though we require only step class annotations, our model achieves superior result in the most stringent metric, success rate, in all the planning horizons. Our model that uses two procedure plans slightly outperforms the model that only uses one procedure plan, indicating the potential benefits of incorporating more procedure knowledge from the probabilistic procedure knowledge graph. Although our model outperforms most of prior works in COIN dataset, It does not secure the top position when considering small planning horizons because coin consists of only 3.9 actions per video on average, a scenario where sequential procedure knowledge is not essential. The advantage of method increases as the planning horizon expands because utilization of plan recommendations from the probabilistic procedure knowledge graph effectively reduces the complexity of long horizon plan. At the inference time, we provide only initial and goal visual states of the task. As reported from the graph conditions, the top part provides the most accurate procedure plan, but by using multiple parts, we can overcome some inaccuracies in the procedure knowledge graph, as shown in the task of building a simple floating shell. Probabilistic procedure knowledge graph improve the performance of our model significantly in all planning horizons. This indicates the necessity of incorporating real-life everyday knowledge, both in task sharing step and managing inherent variability in the transition probabilities between steps. Our graph captures task sharing steps across the entire training domain. For instance, pour water is a step in make Jelloset task, but it can also be a part of other tasks, leading to a step transition from pour water to add fish. Considering the trend of using LLMs, we compare the accuracies between using procedure knowledge graph conditions and LLM conditions in our model. Although there are trade-offs between using LLM-generated recommendations and knowledge graph recommendations, considering the training and testing are conducted on datasets with known activities, knowledge graph recommendations can yield more accurate results. Our method exhibited significantly faster training convergence compared to state-of-the-art prior work PDPP. The training efficiency of our method is achieved by leveraging the probabilistic procedure knowledge graph, which provides valuable context to facilitate the model's learning process. To wrap up, we explored the problem of generating procedure plans with minimal supervision and proposed KEPP, a knowledge-enhanced procedure planning system for instructional videos that leverages rich procedure knowledge from a probabilistic procedure knowledge graph. Thank you.